section 8.3 is on logarithmic functions. This is again mostly review. There's a lot to get through. I'm going to do it pretty fast because you should know a lot of this already. So the first thing we're going to do is we're going to graph some logarithmic functions here. The only thing different with all these functions you can see is the base. We got a base of 2, 4, and 1/2. So let's do that. Now, once you get good at this, you can graph these right away, but for now, you might be having troubles with that. So what you'd probably want to do is change this to exponential form. Remember, this would be 2 to the y equals x. And then we could do a table of values. We could put our x and y, and remember, it would be easier in this case to pick y values. So why don't we go from -2 up to 2, or maybe even 3. So if we put -2 into the y, we get 2 to the -2, which is 1/4. And then we put -1 in here, it's just a flip and negative, you get 1/2. Anything to the 0 power is 1, 2 to the 1 is 2, 2 squared is 4, and 2 cubed is 8. Sorry, it's a bit messy, but there you go. So 1/4 and -2, and 1/2, -1, 1, 0, 2, 1, 4, 2, 8, 3. I think we might have graphed this last time as well, but it goes like this, and down here it gets closer and closer to the y-axis but never hits it. Hey, that's not bad. And we'll put here that this is y equals the base 2 logarithm of x. Okay, let's switch colors and try the same thing, but let's do it with this one. We have base 4. So obviously in exponential form, this is 4 to the y equals x. So again, we can make a little table. Go -2, -1, 0, 1, 2. If you put 4 to the -2, you get 1/16. 4 to the -1 is 1/4. Anything to the 0 power is 1. 4 to the first power is 4. 4 to the second power is 16. You wouldn't even be able to fit that. So we have 1/16 and -2. I mean, this is really, really close to the y-axis. And then we have 1/4 and -1. So it should be on the left-hand side of the blue one. Then 1, 0, just like before. 4, 1. And 16, 2 is way out there, so it goes something like this, and again down like that. So this one is y equals the base 4 logarithm of x. And finally, new color, let's do this one in exponential form. This is 1/2 to the y equals x, so xy. We'll start at -3 this time, go up to 2. So -3, well, that means flipping negative, so it's 2, and then 2 cubed is 8. Flipping negative is 2, and 2 squared is 4. This will be 2. Anything to the 0 power is 1. First power just stays the same, so it's 1/2. And if you square 1/2, you get 1/4. So we have 8, -3, and 4, -2, 2, -1, 1, 0, 1/2, 1, and 1/4, 2. So this time it goes up, still has the same asymptote, but we're going up instead of down, and this comes down like this. And this is y equals the base 1/2 logarithm of x. Now, one thing you might notice is that the blue one and the red one are just reflections of each other over the x-axis, and you would actually expect that. How come? Because what we have written here in red is the same as x equals 2 to the -y. And making this negative, as you should remember from transformations, is just going to be a reflection over the x-axis, just like we got there. Okay, let's summarize. Let's look at the domain of all of these graphs we have there. They all have the same domain, don't they? They all go from 0. Their smallest y value is 0, although it doesn't actually reach 0. So open bracket 0, and it goes up to infinity. Or the other way you could say it is x is greater than, but not equal to 0. So either one of those works. How about the range? Well, for all of them, they go down forever and go up forever. Up, down. So it's all reals in all the cases. So you could say from -infinity to infinity, or you could say y is an element of all reals. The x-intercept. The x-intercept in every single case is the same. It's 1, 0. How about the y-intercept? There is none. Never crosses the y-axis because the y-axis is an asymptote. And in fact, that's the next question. The asymptote is the y-axis. And of course, the equation of the y-axis is x equals 0. And finally, the end behavior. all of them start and end in the same quadrants, from 1 to 4, or 4 to 1. So we'll just put 1 to 4. So the main difference is with the blue and the purple, you can see these are increasing functions. As you go to the right, they're getting bigger and bigger and bigger. Well, the red is a decreasing function. As you go to the right, it's getting lower and lower and lower. So what causes that? Well, it causes what the base causes that. For these bases, they're greater than 1, so it's going to be increasing. This base is between 0 and 1, so it's going to be decreasing. So let's summarize that. If b, or for b is greater than 1, the limit of the base b logarithm of x as x approaches 0 from the right hand side. So this is when b is greater than 1. This is like the blue and the purple. So what's true about that as x approaches 0 from the right hand side? Well, for the blue and the purple, they're both going down, 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 down as we approach from the right hand side, which means they're going towards negative infinity. And the limit of the base b logarithm of x as x approaches infinity, so, well, it's terrible infinity sign. So as you go way, way, way out in this purple and blue one, as you go way, way out to the right, what's happening to the y values of these? They're getting bigger and bigger and bigger and bigger, so they're actually tending towards infinity. Okay, how about for b is less than 1? Well, that's the red one above. And what you can see is that the limit of the base b logarithm of x as x approaches 0 from the right hand side, so remember this is the red one, as we approach 0 from the right hand side, it's going up, 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 up. It's going up towards infinity. And the limit of the base b logarithm of x as x approaches infinity, that's a b. What happens as we go way, way out to the right towards infinity, this is going down, 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 so it's going towards negative infinity. A couple other notes, very quick, because you know this. A common logarithm has a base of 10. You can write it as y equals the base 10 logarithm of x, or you can just say y equals log x, and then it's just take it for granted you mean the base 10 logarithm, or common logarithm, and use the log button on your calculator. Then there's also natural logarithms. They have a base of e. Remember, e is the number, 2.718, etc. I'll put it in brackets, 2.718, goes on and on and on. You can write it as y equals the base e logarithm of x, or you can just write y equals natural logarithm of x. And on your calculator, of course, you use the ln button on your calculator. Okay, we got a big table here of some properties put about logarithms. The base b logarithm of b to the x equals x. Okay, does that make sense? Here's a little proof for you. Remember when we have logarithms written like this, we could scuttle that x out front, so we could have x log b, like that, the base b logarithm of b. Well, if you just look at this bit, what does that equal? B to the what equals b? B to the 1. So this whole bit here is equal to 1. So you get x times 1, which equals x, just like we said right there. Similarly, you could write it for natural logarithms. That's what I'm going to do over here. That the natural logarithm of e to the x equals x. Same exact reason. Okay, next one. B to the base b logarithm of x equals x. Okay, to prove this one, let's take the logarithm of both sides and let's take it to the base of b. So on the left hand side we'd have the base b logarithm of all of this, b to the log bx equals the base b logarithm of x. Then we could take this exponent here and scuttle it out to the front, so you get the base b logarithm of x times the base b logarithm of b equals the base b logarithm of x. Now this bit right here is exactly the same as what we did up there. B to the what equals b? B to the 1. So this right here equals 1. And what we're left with is that the base b logarithm of x equals the base b logarithm of x. It's totally true, so what we started with, what must be true, we've proven it to be true. Similarly over here, if you have e to the natural logarithm of x, it equals x. Okay, next one. The base b logarithm of 1 equals, okay, we could get this, b to the what equals 1, b to the 0 equals 1. And similarly, the natural logarithm of 1 has to equal 0, because e to the what equals 1, e to the 0 equals 1. Finally, the base b logarithm of b equals, that's what we talked about up here. Should have done this one first, I suppose. It equals 1, and same with this. Okay, one last thing to look at. We're going to look at change of base formula. And the way that works is the base a logarithm of x, if you have something like that, is exactly the same as the base b logarithm of x divided by the base b logarithm of a. So you see what we've done is we've taken a logarithm which has a base of a, and we've written it as another logarithm. It's actually a quotient of logarithms with a base of b. We've changed the base, and sometimes that can be very useful. Related to that, the base a logarithm of b is equal to, now if we use change to base and put base b for both top and bottoms, we'd have base b of b over logarithm of base b of a. Well, if you look at this top part, that's exactly this, so you get 1 over the base b logarithm of a. So there's another property of logarithms. If you have the base a logarithm of b, it's equal to 1 over the base b logarithm of a. Okay, it's not used all that often, but it's kind of a nice one to know as well. Okay, find the domain of the function f of x equals the common logarithm of x minus 3 and sketch its graph. So one thing to remember, I'll write it in here, the argument must be positive. So what we can say then is that this bit, the x minus 3, has to be greater than 0. In other words, x is greater than 3. So there's your domain, x is greater than 3. In terms of the graph, if you think of this compared to the graphs we've already drawn on the other side of the page, what's the only difference between this graph and like the graph of log x? The only difference is it's been translated 3 steps to the right. So instead of your asymptote being at the y-axis, it's going to be 3 steps over. And actually that matches very nicely our domain, which says it has to be x is greater than 3. Remember that we said that the graph always went through the point 1, 0 on the other side of the page? Well, 3 over from that is 4, 0, so that looks good. And then since the base is 10, we know it's going to be the type of graph where it goes down towards negative infinity. So it's going to go down like this, and it's going to come up like that. Now, have I done it exact? No, but this is a pretty good idea of what it would look like. So this point right here would be 4, 0. Another useful amount would be when this argument is equal to 10, because 10 to the 1 equals 10. And that would be when x is 13, right? If you had 13 in here, 13 minus 3 is 10, and 10 to the what equals 10? 10 to the 1. So in other words, 13 and 1 would be another point. So I don't know, this is way off, but I could just put the point 13, 1 there. That'd be another point it goes through. But that's not so important. I'm just really interested in you knowing where the asymptote is, knowing whether it goes up or down. So this looks pretty good. Okay, next one we're going to solve this equation. What we want to do here is to take logarithm both sides. Now, what kind of logarithm we're going to take? Well, since this is e, we're going to take the natural logarithm. It's going to make it easier to cancel some stuff out later. So both sides take natural logarithm. Then we're going to scuttle the exponent down, so we'd have 3 minus 2x all multiplied by the natural logarithm of e. Okay, remember, natural logarithm has a base of e, so e to the what equals e? E to the 1. This bit here in yellow, this bit here, the circle bit, that equals 1. So all we're left with then is 3 minus 2x equals the natural logarithm of 4. We just have to solve that. How about I'll move the negative 2x over and move the natural logarithm of 4 over. So I get 3 minus the natural logarithm of 4 equals 2x. Divide by 2. X equals 3 minus the natural logarithm of 4, all divided by 2. If you put it in your calculator, which it's not necessary at all, in fact I kind of discourage it, you'll get approximately equal to 0.807. Okay, last question. Find the limit of the natural logarithm of 4 minus x squared as x approaches 2 from the left-hand side. So if we just look at this bit, the 4 minus x squared, and if we put a number just a little bit smaller than 2 in there, we're talking like 1.9999, right? And then we square it. A number just a little bit less than 2 that's squared is now going to be just a little bit less than 4. So when we do 4 minus x squared, we're we're going to have 4 minus a number just a little bit less than 4, which means we're going to have a very small positive. Well, the next thing you want to do is you want to think about the base of this. The base of this is e, and e is 2.7. So in terms of our graph, the ones that were greater than 1, if we look back here, like the blue one and the purple one, remember their graphs, they went down like this towards negative infinity at the asymptote and then increased after that. So again, we would have something that looks like this. So it's like looking at just the right hand side of the asymptote, and from the right hand side of the asymptote it's going down towards negative infinity. So maybe just up here I'll put negative infinity, and that's your answer. Okay, that's your review of logarithms. Time to start doing some calculus with them. You're simply